Hello and welcome to lesson 2.2 definite integrals. This is going to be day 2. Now this lesson has been put together because I find the textbook doesn't give a good enough set of examples and ideas of how to change summation notation into integral notation. And the AP exam does require you to know both how to do this using left Riemann sums and right Riemann sums and various different formats that they don't present in this textbook. So this lesson is an attempt to actually help you out in understanding this. So first off, we're going to start with this notation. The limit as n approaches infinity, as the summation goes from k equal to 1 to n of f of xk times the change in xk. Now, we're going to look over at this function to the right, given here. And you can notice we're taking the summation and we're changing it into its integral notation that we have there. So it's going actually from the value of a to the value of b. And we're going to talk about left Riemann sum and right Riemann sum changes in a moment. But basically, what you're doing is you're going from the values of a to b. You're taking that and you're splitting it up into n subintervals. So that's what's going to give you this b minus a over n is your change in x values. That's how those related there. And then we're going to have where you have your function occur based on whatever your a value is plus k times change in x. Now the k value itself might actually change to k minus 1 if it's a left Riemann sum compared to a right Riemann sum. But that's basically the difference. And once you've got that, all you're doing is you're just changing this expression into this expression. So the idea is sometimes you're given these limits, the summation limits in that format, and you're changing it into an integral, or vice versa, you're changing an integral into a summation limit. And as already mentioned, left Riemann sum just has the value k minus 1, and a right Riemann sum has a value k as a subscript. That's the only difference between them. They don't use midpoint Riemann sums because there's no such thing as midpoint Riemann sums, and as n approaches infinity, these two approximations turn out to be identical and indistinguishable from each other. So let's look at our first example. The first example turns out to be one of the easier ones that I think of. So right here, you already notice that 5 over n, oh, by the way, we're going to take this summation, we're going to change it into a right Riemann sum. 5 over n turns out to be your value for your total values from a to b, that is 5 units, and you're separating it into n intervals, or n subintervals. So that means your values of b minus a over n is equal to 5 over n. But specifically, you want to have a lower bound of 0. So that means your value of a actually has to be 0. So the only way that will work out is if you have it 5 minus 0 over n. So now you have your a value as 0 and your b value as 5. Because you have that way, now you can change this into an integral on the domain from 0 to 5, or you're integrating on that domain 0 to 5. Since your function is specifically 4 times the function x squared minus 3, all you have to do is slap on this dx at the end, which is specifically talking about the actual change in x values that you got there, then this is your integral. Now if you want, you can change that so that you can bring out the 4, because that's just a constant. It's not going to change the function. And you can write it like this. 4 times the integral from 0 to 5 of the function x squared minus 3 with respect to x. Okay, so let's take a look at our next example then. Okay, so what if we want to change it? What we want to do is we want to express the following definite interval to have a lower bound of 0 instead of 3. And as you can see, currently it does have a lower bound of 3. So first off, what does this actually mean? Well, I'm going to draw a little sketch over to the right of what this function actually looks like. So this is a cubic function, x minus 3 cubed times 2. So that means it actually goes for the value 3 on the x-axis. Oh, let me actually move that over. Let's put 3 about... Oops. Let's put 3 about here. And now we draw our function. Oops. That should go right through there. Like this. Okay, now let's say 8 is just somewhere over here. I'm not going to make it too much bigger. But what that's doing, this integral is actually finding the area underneath this curve. That's what it's looking at specifically. And this is the function right here, f of x being equal to 2 times x minus 3 cubed. That's our function. Well, what we can do is what we want to try to change. So we want to try to change it. I'm going to redraw this kind of thing right here. We're going to try to change it. So now this drawing of this graph goes right through 0 instead right here. We're going to have a different value over here. And we want the area to be the exact same thing. Well, if the area has to be the exact same thing, that means the difference between 3 and 8 is 5 units. So this has to be 0 through 5. Our function would now be the function, let's call it g of x instead. And that would just be 2x cubed. So, how we change this? Well, we realize that this is the integral from 0 to 5 of 2x cubed with respect to x instead. And you'll see that they are identical in expressions. It's just one's a translation 3 units over from the other one. So we can see that these work out that way. So these are the basic ideas of the integrals first of all, and how to change them into integrals. Let's get something a little bit more complex here. So what we're going to do is we're going to show the summation on the left is actually equal to the same integral, or equal to that integral on the right hand side. Okay, and we're going to do a little bit of analysis here. Well, first of all, realize this has k, these values are just k. So this is actually a right Riemann sum. That's something that we got to notice for sure. Okay? Next part, look at this 5 over n part. What we could do is we can set our change in x value to be our 5 over n. If that's the case, we can also set it as 5 minus 0 over n. And you can see that right there is part of our integral now. So that already has a value of 0 and a b value of 5. So that's something that we've already got there. Well, if that's the case, then notice that the 1 plus 5k over n part, well, that's just equal to 1 plus k times our change in x value. And that means this 10k over n is equal to 2k times our change in x values. So if that's the case, and we can assign every, let's say, k times change in x value as our x values. So let me state that. Let k times the change in x equal our x values. Then, now we can change our limit as n approaches infinity for the summation of k equal to 1 to n of 10k over n times the square root of 1 plus 5k over n times 5 over n. Well, this is now equal to the integral from 0 to 5. So this part becomes 2x times the square root of 1 plus x dx. And there we get what we want exactly as we were hoping to see it. So, hopefully that makes perfect sense to us now. Okay, so let's try our next problem. And with this problem, you can see it's the exact same expression on the left-hand side, but the integral is different on the right-hand side. So how can we go about doing this? And what we're going to try to do is something very similar to what we just did with our previous problem. But we're going to change some values, just slightly. So instead, what I'm going to do is, instead of me taking the 5 over n as our value, I'm only going to take the 1 over n aspect and make that equal to the change in x value. Well, if that's the case, realize that 5 over n is actually 5 times 1 over n. And that means our a value would be 0 and our b value would be 1. Okay, so now that's got that part that we wanted to see. Okay? Remember, that's what we're trying to make look like happen. Okay? So now that means this 1 plus 5k over n aspect turns out to be 1 plus 5k times the change in x, and this 10k over n turns out to be 10k times our change in x. Again, if we make it so that our change in x value, or sorry, k times change in x value is our actual x value, because that's where our x value would actually occur based on whatever values we have, then you can now take it so that this limit as n approaches infinity for the summation from k equal to 1 to n of 10k over n times the square root of 1 plus 5k over n, 5 over n, well, that's equal to, first 0 to 1, this is now going to be 10x multiplied by 1 plus 5x dx, and we're multiplying by 5 here because of the extra 5 that we missed multiplying by the 1 over n. So that extra 5 you can take right out in front of the expression. And you get what you wanted to see. Now, it's a worthwhile note to mention that you can always use your value of a to be this first value that you're adding right here. You just have to take into account if it affects this value in any format. So you could actually start going from 1 to 2 if you wish, but realize that based on our expression up here, looking at our original problem, where was I? Right here, this value of a is the same value of a that's in my integral. So that can always change and make those notes for yourself. Okay, so let's take a look at our last example. We'll see if you can figure that one out. So please realize this last one is a left Riemann sum that we're looking for. So it's asking us to now take the integral and change it into a left Riemann sum. Okay? Now also notice that this value goes from 1 to 7. So that means we have to have our a value. Our a value is actually 1. And that has to come into play when we're looking at how is it affecting our x values. Okay, so if our a value is 1, that means b is 7. So now that means the change in x values are going to be 7 minus 1 over n, or 6 over n. So that's going to be our change in x values. That's how it's going to change based on that. So that means what we have is for every our xk value are going to be 1 plus k minus 1 times our change in x values, or 1 plus k minus 1 times 6 over n, if you want to write it like that. So what we can do now is we can change this integral back into a summation notation. So let me write the integral again. 1 to 7, 4 ln x plus 2 dx. Now this changes into the limit as n approaches infinity for the sum going from k equal to 1 to n for the function 4 natural logarithm. Now here's where our x value is. It's 1 plus k minus 1, 6 over n. That value, we've got to take that and we've got to add 2 to it and the bracket there, and then we got to put 6 over n right here. And there we go. So, this concludes this lesson.